So this is Physics 2112. We're going into Chapter 14 on inductance. Inductance. Okay, so inductance. Well, first thing we're going to do is start off with mutual inductance, and hopefully it'll go a lot better than what I was saying earlier in class, because that just didn't go well. So what is mutual inductance? Let's just lay that down. Okay, mutual inductance. This is how, this is how we quantify the effectiveness of one inductor on the other. On the other, and I'm saying 1 here, so let's just say the other is 2, okay? Great. So, it could also be on the inductor itself. Okay, and so we'll look into that. Okay, so we have inductor number 1. All right, so let's do inductor number 1. And I'm basically drawing what they drew in the book, only hopefully I'm going to do a better job. We're going to have some current. So this is inductor 1. It's got current 1 going into it. And the current, this isn't the B field, this is the current. So the current's going to go in this direction, okay? And all the way through this thing, there's little wires that are wrapped around each other. In fact, there are N1 wires, okay? And they're all going in that direction. At the bottom side, it's a loop. So at the bottom, we've got these guys coming back this direction. This is the current coming through this way, and it'll go back up to the top. Okay, so what does that do? Well, we all know what that does. Each of those guys add together to create some B field. All right, so we've got some B field coming through, B field coming through, like this, and that's our B field from 1. Okay, so that's all coming through. Okay, that's fine. That's inductor number 1, we call it, okay, with current 1, number of loops 1. So right over here, we're going to put inductor number 2. Inductor number 2 has a different shape. It's not quite as big or whatever. It has a different number of coils. It also could have current going through it, I2, and of course its current is going in. I'll put a 2 here, thing 1 and thing 2. So that current's going like that. This is coming back up in all the little wires, going back up to the top. Okay, so we've got current going into the page on the top and out of the page at the bottom, and it's a circle. In fact, I'm going to draw our circle. kind of like this. Wait, I want this one to be solid too. Okay. So this is our circle. On the inside of our circle, right in here, that inside here, let's get rid of the first one. Okay, let's do our area here instead. So our loop is going all the way around, okay? And this is our area 2. Okay. Good. So there is a flux through area 2, okay? So we're going to call this flux phi 1, 2. Okay, why? Because it is the flux of 1 onto 2. Okay, so it's the flux of B1 on area 2. Okay, so this is my nomenclature. I don't know if this is how they do it in the book. I don't want to think about what they do in the book. Today I was trying to work with the book in class, and the whole thing, it wasn't working. I fell apart. It wasn't everybody's fault. It was mine. So this is my nomenclature. Okay, so we've got B1 on A2. All right, that is phi 1, 2. All there is to it. Okay, so we've got N2 turns over here, N1 turns over there. We've got current I over there, current I over there, I2 over there. This B field comes from I1, okay? So I1 generates that B field, okay? So this is number 1 affecting number 2, okay? All right. So it's always 1 acting on 2, okay, for me. So the mutual inductance, we're going to call, I want to know the mutual inductance of 1 onto 2, okay? So I have to have area 2, n times area 2. So I'm going to do n2. And the phi 1, 2. And we're going to divide out by I1. Okay, how does this come about? How does this come about? Also, you can define this yourself if you want. You can do it any different way you want to. It doesn't matter to me. I'll figure it out. If I have to figure it out on your homework, I'll do that. And if I don't do it right, then just come talk to me and say, hey, you didn't do this right or whatever. I was really saying this. Okay, so what is mutual inductance? Let's just talk a little. Can we talk? Okay, so what is mutual inductance? The first thing you have to think about is, what is phi? All right, and we all kind of think we know what phi is, right? It's the B field through an area. Of course, that there could be an angle between the B field and the area normal. That's fine. So let's not worry about that. We'll use a perpendicular. And we'll get that phi is equal to B times A. But we can do what we did here, okay? So everything's perpendicular. Don't worry about that. And we will say that our phi 1, 2 is equal to B1, whatever the B is from 1, hitting the area 2, going through. So what is that flux? Okay, so if we have N coils that carry I1 current in them, then that is going to generate a larger B field. So we could have a lot larger B field because I1 has N1 coils in it. Okay, so that will generate more. What produces the I1 to B field? So B1 B field is produced by I1. Okay? I1 produces it. The mutual inductance of coil 1 on coil 2 then is, we could say that if we multiply I1 times that mutual inductance, then we'll have N2 times the phi going through. So we really want this guy right here. And that leads us to this equation. Okay? So, I don't know if that is clarified anything or not, but anyway, that's how it works. So, units of mutual inductance. If you look at how it works, we've got B times A, all of that. That's going to give us 1 volt times a second over 1 amp. Okay, that's what we get on the N2I1 phi 1, 2 side. Okay, these are our units. Okay, 1 volt second divided by an amp. So that happens to equal 1 Henry. Okay, we call it a Henry. Or it's measured in Henries. I don't know. If you have more than 1 Henry, you have Henries. So, I don't know. We're just trying to keep everything nice and easy for all the physics students out there. So we deal with Henries. Okay. However, I want to come back and emphasize something. And we kind of did this in class, and it seemed to make sense at the time, and hopefully it does now. This whole thing could be done in reverse, okay? Because we could have a B field that's generated here. Let's erase this B field. Get this out of here. Nobody likes you, B field. And then we'll have some area 1. Area 1 here. And a B field from 2 going through. Okay, so B field of 2 going through this area. All right? And that same thing would occur and give us M21 equals N1 over I2 times the phi of 2 and 1. So, great. Now, everybody knows that equal and opposite thing, right? With Newton's third law, equal and opposite. Well, guess what? That still applies here. Okay, so we can come down here and we can say that the mutual inductance of 1 on 2 is equal to the mutual inductance of 2 onto 1. Therefore, we just have this mutual inductance, okay, measured in henries, in 1 Henry or many henries. So we don't have to really worry about all of that, all of those things. We can go through and do it for one, and then we've got it for both, okay? So, cool, super cool. So what does that mean? What does that mean? What is the meaning of this? That means that N2 over I1 times phi of 1, 2 is equal to N1 over I2 phi of 2, 1. And both of those things equal this M. So these are more equations that we can use if we happen to know currents and we happen to know the number of coils for the winding. Okay, these are the turns or winding. And the flux, the magnetic flux. So we only need to know those three things, and we can get our mutual inductance or inductance from one to the other. Here's one way to keep things. Here's one way to keep things together. Okay, so N1 and A1 go together. Okay? N2 and A2 go together. So these things go together. And then on this side, I1 and B1, and then I2 and B2 go together. Okay? And they flip for the others. Okay? So it crisscrosses. Crisscross. So these go with this, and those go with that. Let me see. Just want to make sure that they do crisscross. N2 and B1. N2 and B1. Right. So they have to crisscross. Okay? So good. So they all go together, but they crisscross. So those go with those, and those go with those. Okay, so that's how they all go together. That's how they fit. And okay, great. Take a breath. Hit pause. Whatever you want to do. Go to the bathroom. Come back, and we can talk about the EMF in terms of mutual inductance. So we know that the EMF is minus the derivative. I'm going to stick N in there because we're always going to have N coils from now on, okay? But is the N going to change as a function of time? No. So it really doesn't matter. So we all know that this is the case, right, for any of those coils. And now we can just insert our minus ddt. We'll put in our numbers. So we've got N2, for instance, and that means I'm going to be dealing with phi 1, 2. All right. So I'm going to take, that's this right here, by the way. So I can get an EMF from that. And this is the EMF for coil 2. Okay? Because we're dealing with, let's just come back up here. Well, it's obvious. We're dealing with B1, right? So if we're dealing with B1, we're dealing with A2 and B1. Okay? So that's for coil number 2, the EMF inside that coil. Let's even put a little thing here. Coil number 2. EMF for coil number 2. Good. Here's what this is equal to. I don't know if you guys already can see the end of the punchline on this, but if we come back to here, this is equal to our mutual inductance times I1. So cool. And there's some beauty to this. What is the beauty of this? Well, the EMF in coil 2 is this mutual inductance going to change? No. That's all firm, okay? This is a constant. Nothing's moving. Everybody's staying still. It's just wires and areas and all that stuff is staying still. But I1, however, is a function of t. So we end up with m, well, minus m, times the derivative of I1 as a function of time. That is the cool part, okay? So all we need to know is what was happening on the coil number 1, take its derivative for I1, and then we know what the mutual inductance is. We can go through and put in all those numbers, the areas and all that stuff. And then we've got it. So all you have to do is take the derivative of that first current. Or, and let's properly call this EMF 2. Okay? Or we can do EMF 1. Same thing. We just say EMF 1 is equal to minus same mutual inductance that we had, because this is the same old two things, and then we're just going to take the derivative with respect to time of the second coil's current. And now we've got E1. Pretty easy. It makes a lot of things nice. We can see what that EMF is generating current in each of the coils. All right. So now we really have to study inductors, okay? Mutual inductance and inductors. That is that's the whole thing. So let me, I want to be clear about this. So we've got mutual inductance happening, okay? What do we call these things? This thing is an inductor. This thing is an inductor. So these are inductors, okay? And we are going to talk about straight up looking at nothing but inductors. So let's draw out an inductor. I've got an EMF battery thing, whatever you want. So don't hurt yourself. You can go back and look in the book if you really want to, and it'll help, maybe. It should help. The book's pretty good. And we've got some resistor in our circuit, and we're going to drive it. We're going to flip the switch closed, and we're going to drive it, and that means that we're going to have some current flowing in this direction, okay, around our inductor, okay? But this is an n equals 1 inductor. So we've got n equals 1. I don't know why. Okay, great, whatever. N equals 1 inductor. What is the B field that's happening here? Well, on the inside, we can put our thumb along I, our fingers curl into the page here. And on the outside, if you want, you'll see that you get this. So those are the B fields and E fields. Not all the fields. I'm just kidding. It's just the B field. Stop it. I need to eat dinner. Maybe I'm tired. Okay, who knows? All right, but here's this thing. We've got a radius R, and that radius means that we have some certain area, and we all know that, pi r squared. Okay, so whatever r happens to be. Our flux, we know what our flux is equal to. It's our B field times our area. And the flux is proportional to the I generating the B field. Because how do you generate a B field? You have to have moving charges. It's the only way. Okay, moving charges generate your B fields, and this is how that happens. Okay. So this proportionality, okay, we give a name to. So there's a proportionality. So we say that phi is equal to L times I. Now, we don't know what L is yet. Nobody knows, but we're going to figure it out, okay? So don't even trip, dog. We're going to get it. But this L is the proportionality, okay, for generating the B field. All right, so that goes through our flux. So what is L? L is our inductance. Okay, so this one loop has inductance, okay? And that loop has an inductance of L. So we can then say this solidly, and now all we have to do is go around and figure out what all that happens to be. Now, just real quick, I want you guys to know that if we have n loops, we have n times phi, okay, because you'll have phi n times, all right? So n times phi, that'll be equal to our inductance times I, all right? This leads to our phi equals I over n times L. And that's if we had n equals or n greater than 1. Okay, however many you want. Now, L is positive definite, always greater than 0. Okay, so always positive, and it's called the inductance. Okay, L is the inductance, always positive. So be like the inductance and always be positive. That's a good moral for me. I need to listen to my own advice. Okay. Let's get into it a little bit then. Let's look at our EMF. That's equal to minus our n times d phi dt, which is equal to minus our n over n times L di dt. Okay, well, the n's cancel, which is kind of handy. And we're left with, where's my negative sign? Negative L d dt of our current. And voila, L is our self-inductance. So self-inductance. So it's not just our inductance. I could keep inductance. That's handy. Let's keep that. It's a nice inductance. Is equal to the self-inductance. So each thing, doesn't matter how you do it. You can come in and you can draw a loop like this. You can come in and draw many loops, like a big long solenoid. You can do whatever you want. From n equals 1 to a certain n per unit length. You can do however you want, but you have a self-inductance L for this item, okay? No matter what happens, that item has L, all right? And to make, I'm gonna just clean it up a little bit. Makes a nice neat inductor there. Cool. Okay, so that gives our inductance L. It's our self-inductance. It's just a thing that has inductance, okay? And it will induce or be induced. So let's try and calculate L. Let's do some work with L, okay? So let's do a little work with L, and we want to calculate L. So what do? We can use this equation that it equals our EMF and just solve for it. So that's nice. Let's do that. So if we take our EMF and we divide by the derivative with respect to time of our current going through our L. This isn't another current anywhere else. It's the current going through our loop, okay? So just to reiterate, this loop right here has current going through it. This one right here, current going through it. That's the current that's going to change and give us our self-inductance, okay? So, good. All right. Now, if you noticed, somebody out there is probably like, oh, you dropped your minus sign. Look at you and your minus signs. Well, L is always positive, okay? If it exists, it's like mass. If it exists, if the object exists, then it exists and it's positive, okay? In other words, ooh, I need to write that down. Friction. This is a frictional thing, by the way. Oh, okay. Friction happens. Entropy happens. All right, so L is always positive. So since it's always greater than 0, do we care about whether we're dealing with this or what? No, we don't care. We just want to know the value of the thing. And then whatever the value of the thing is, then we've got it, right? So it really, really, really doesn't matter. So we can then go, this equals this, and we can say that the derivative of I of t is equal to the derivative of I of t. And we're golden, right? So we don't have to worry about our positives, negatives, or any of that other stuff. So now I'm going to just write this final self-inductance equation. And I'm going to write it like this because it's, do I need to, if that's positive, that's negative. It really doesn't matter. So we can just write it like this, or we can just take the absolute values of the items themselves. So you can do the absolute value like this, or you can do the absolute value like this, however you want. I like working with positives at all times. So me personally, I would just take the absolute value of this, and then I would take the absolute value of this, and that would give me my L. That's how I would do it. Okay. Now I don't know if you guys remember, but we went through and we talked about what are symbols when we're drawing circuit diagrams. So like we had the a battery, right? We had a resistor. We had a capacitor. We had, what else do we have? Well, we have switches and light bulbs and, all kinds of great things. Guess what? We now have an inductor. And I may have told you back then about inductors, and I just said we'll come back to it. I may have drawn one, but the symbol for an inductor is this guy. So this is the symbol for an inductor. It has a certain value. Okay, it has a certain value. What is the value in henries? Oh, I dotted my Y. Good work. Okay, so henries. Of course, that's equal to just an H, right? So good. Now, it has a value, and it's always positive, right? Positive definite. So always greater than 0. And here's kind of what you might see, all right? So here's point A, here's point B, here's some inductor. I don't want to do all the squiggles all the way down the line. We'll have some current going through the inductor from A to B. That current, the derivative of that current is greater than 0. Okay? So the derivative with respect to time of that current is greater than 0. Gives us an EMF. Oh. So I'm going to just rise up here a little bit. Leave it like that. When the derivative is greater than 0, our EMF goes in this direction. This is self-inductance, okay? Self-inductance goes in that direction, which is equivalent to a battery with a positive side there and a negative side there. Okay? Now, let's do the same thing. We've got the same 2 points. We've got a same inductor, A and B. We've got current going this direction through our inductor. However, our d dt of the current is less than 0. We're going to have an EMF that goes in this direction. Can you guys tell me why? Can you tell me what's happening? Do you think it could be a Lenz's law situation? If our B fields are generated by the moving current and our inductance is occurring, it has to be a Lenz's law fight that is driving a current the same way, okay? It's fighting this change in current, okay? That's it. So EMF declining and actually pushing more current through the loop if our current is declining. If our current is increasing, then the EMF is trying to slow down that amount of current going through. And I'll just put a little equals a battery that looks like this, where it's negative here and positive. So we're going to stop for now, and we'll come back. Okay.